Let us begin our today's lecture, and we continue to study Gaussian random vectors. Today, our aim will be in the investigation of the properties of Gaussian random vectors. Namely, we will discuss cases when it has density, and we will start investigation of functionals from Gaussian random vectors. As we mentioned at the beginning of our lectures, it occurs that there is powerful and from other side simple tool to investigate functionals from Gaussian random vectors in a similar way as we did this in real analysis with the functions which we differentiated and make some conclusion about its properties. So let us recall what is the main object of our considerations now. We consider random vector psi with coordinates psi1, psi_n in Rn, and we said that this vector is a Gaussian vector. If element of Rn such scalar product lambda psi is Gaussian random variables. We know already that distribution of such a vector is characterized by two objects. One is mean of this vector, is simply denoted by xi, and this is a vector which consists of means of coordinates. And another one is the covariance matrix of this vector psi, which is a matrix consisting of the elements of the kind expectation of xi minus mi, xi j minus mj. Ij are numbers of points. And it occurs that in terms of these two objects, the characteristic function of this vector can be written as follows. If we now consider expectation of exponent I lambda psi, then it will be the following expression: lambda m minus 1/2 in quadratic form of covariance matrix from lambda. From this point of view, we see that distribution is uniquely defined by the vector m matrix A, and we denoted it by the symbol which is similar to one-dimensional case. So we use such notation for multi-dimensional Gaussian distribution with mean equal to m and covariance matrix A. Now we are going to discuss the existence of the density of such a vector. To do this, firstly, recall that last time we found some useful formulas for transformations of Gaussian vector, which leads again to Gaussian vectors. Namely, if we have such vector psi, which has such distribution, then we can consider its transformation like new vector eta equal to, for example, matrix B xi plus some vector C. Then it occurs that eta again is a Gaussian vector, and moreover we found its characteristics. Namely, we found that it will have mean like Bm plus C, and the covariance matrix like B, A, B star. And this is a very important relationship because it allows us to do a lot of things and conclusions. Firstly, it will give us possibility to construct Gaussian vectors with fixed distribution from special one. Maybe you remember that in case of random variables, we call Gaussian distribution with zero mean and unit variance by the standard Gaussian distribution. Let us do the same in multidimensional case. So let us try to fix one standard distribution among all set of multidimensional Gaussian distributions. So let us consider special case when n equals to 0 and A equal to identity matrix. So let us write the following definition. Such distribution is called standard. Let us try to find properties of this distribution. Namely, let us start from the characteristic function. I will denote a vector xi, which has this distribution, and then its characteristic functions have the following kind. Is exponent minus 1/2 norm of lambda square. Yes, because norm of lambda square is exactly quadratic form generated by the identity matrix. Let me continue with this equality and we will write this norm in coordinate form. Then one can get the following: minus 1/2 of the sum of k from 1 to n lambda k squared, which is of course equal to the product relatively to the sum in the power of exponent. We have here product from k equal 1 to n e minus 1/2 lambda k squared. In this expression, one can recognize product of characteristics function of coordinates. Why? Because we are discussing a case when our covariance matrix is equal to identity matrix. So if I take, for example, psi k, it has the following characteristics. Its mean is equal to 0, and its variance is the diagonal element of the covariance matrix related to the row or column K. And it is easy to understand that it is 1 now. And if we consider exponent expectation of E lambda k psi k, due to this relation, it is equal exactly this multiplier, minus 1/2 of lambda k squared. Since then, one can see that characteristic functional of our vector is equal to the product of characteristic functionals of its coordinates. This mean, due to well-known fact from usual probability course, that coordinates of our vector are independent. So one can say that coordinates of our vector are independent. Psi1, psi n are independent. By the way, here we make a conclusion, which is a partial case of well-known and useful statement that if we have jointly Gaussian random variables which are non-correlated, then they are independent. It is useful to note this property and prove it exactly in the same way as we did here for this partial case. I will use this property in the future. Since we have independent coordinates for our standard vector, standard Gaussian vector, and these coordinates have a density, then it immediately follows that psi itself has density in the space R. So let's write it. Now we understand that psi has a density. And even one can find it easily like a product of densities of coordinates. So the density of psi, p psi x, is equal to the product from k equal 1 n, and here I use just density of the one-dimensional standard Gaussian distribution. We already remember it. It has a simple expression like this one, minus 1/2 of x k. So finally, one can rewrite this as a product, and one can get here 1 square root of pi in n power, and it's a dimension of our space. And here is minus 1/2 of the norm of x squared. It is a density of the standard Gaussian vector in the space R. By the way, it is good to note here that such kind of probability density was discovered by Maxwell when he studied distribution of velocities of molecular of ideal gas in the large volume. It occurs that this velocity, this distribution has some geometric properties, like its coordinates are independent and it is invariant under rotation. And it immediately leads to conclusion that we have distribution like this. So sometimes you can even find in statistical physics the notion Maxwell distribution instead of more common for us Gaussian distribution. So we have such a density, and now let us think how one can construct from a Gaussian standard vector with arbitrary Gaussian vector with arbitrary parameters, and how the density will change under such construction. Let us start from a very partial but essential for future consideration case. So let us rotate this Gaussian vector. What I mean under rotation in the space R. Let us consider a matrix U, which belongs to the set R. So, from the point of view of functional analysis, this is continuous linear operator acting in the space Rn. And I will suppose that this matrix are orthogonal. It means that its joint is equal to its inverse. So it's definitely its inverted matrix, and its inverse coincide with its conjugated. You see, for some people it is boring to jump into functional analysis from this place. So let me recall you what does it mean for coefficients of this matrix. It means the following, that U is consisting of the such coordinates U11, U1n, UN1, UNN, that for any case which is equal to 1 to n, we have that the sum from case from G equal 1 n U JK square is equal to 1, and the sum from J equal to n U JK1 U JK2 is equal to 0 immediately if K1 is not equal to K2. The good example of such matrix in two-dimensional case is a matrix of rotation. So in case of n equal to 2, one can consider, for example, such matrix cosine t, sine t, minus sine t, cosine t. And of course, everybody recognize here the matrix of rotation on the angle t around the origin. Due to this fact, in general, this orthogonal matrix also can be viewed as a generalization of rotation. This unitary matrix has good properties. It keeps angles and lengths in the space. Namely, if one have two vectors x and y, then the scalar product ux uy is equal exactly scalar product xy, and as a partial case, one can check that norm of ux is equal to norm of x. So this is a transformation of our space, which keeps angles, length, which keeps rigid body remain to be in their shape. Yeah? So let us now apply such a generalized rotation, orthogonal transformation to our standard Gaussian vector. Let us take a standard Gaussian vector. And consider mu vector eta, which is obtained like application of our orthogonal transformation to initial standard Gaussian vector psi. Then, due to our general formula, one can say that eta is Gaussian with the known parameters. We know that eta has normal distribution with mean 0, because we have here nothing, and here we have 0. So with mean 0, and the following covariance. Yeah. Let us continue. Here, identity matrix will disappear, and we remember that conjugated operator is just inverse. So we understood that this is again identity matrix, and due to this, one can say that standard normal distribution is invariant under rotation. By the way, it is expectable because as we have seen, characteristic functional of the standard Gaussian distribution, its density depends only on the norm of the vector. In case of characteristic function, it was norm of lambda square. In case of density function, it was norm of x square. So we have such an interesting partial case. Now let's go to the general case. And suppose that we are transforming our standard Gaussian vector psi by affine transformation, which we discussed. So we have standard Gaussian vector. We consider new vector eta, obtain it as we said, like affine transformation plus C. And now let us try to find density of. I will try to use a change of variable formula. So first of all, let me use the framework from the beginning courses of analysis from the university, where we usually say, let the transformation will be one-to-one. Yes, this was a technical condition, but it was very helpful in the writing of the change of variables formula and also in the proof of this formula. So let us start from this case. So we want to have transformation x to bx plus c to be one-to-one. Is a rejection. When is a rejection? Of course, when B is invertible, yes. So it is equivalent. It is equivalent that B is inverted. And it is equivalent that determinant of B is not equal to 0. You see, here we use the privilege of a finite dimensional case. Sometimes for some of you it seems to be boring. We still are working in Rn, and when we will jump to really hard things like Hilbert spaces, white noises, and so on, we will do this. But now, you see, it's good to have such a characteristic of invertibility. So let us consider this case and consider such a transformation. Then, of course, we can discuss the density of vector eta using change of Reb's formula. How we'll do this? Let us discuss a probability that eta belongs to some set delta. As I mentioned, we always suppose that we are working with good Borel sets. So now delta is a Borel subset of the space Rn. Let us consider this probability. It is equal to probability that bxi plus c belongs to delta. It is equal to. Now I will apply the inverse transformation to the set delta. So I will use the following notation. I will say that this is the same, the probability that a vector psi, our standard Gaussian random vector, belongs to the set here b minus 1 from delta minus c. What does it mean? This formula must be read point-wise. Namely, we take every point from here, then do this operation minus c, shifted on minus c, vector minus c, and then apply this operator. And we do the same with any point of this set theta. So I think that this notation is clear. and it is also clear that this is also Dorogovstev. Yeah? Since then, I can continue and write this probability using probability density of our vector set. I will get the following formula. It will be the integral with respect to this set b minus 1 delta minus c. And here is the density 1 square root of 2 pi in n power, and the dimension of our space, multiply the exponent minus 1/2 norm of x square dx. Then what I'm going to do, I just want to have here delta, because I am looking for the density for vector theta. Since then, I will apply here change of variables. Namely, I will introduce new variable, and it will be y, which is exactly d of x plus c. And here is the place which I mentioned for the simplest change of variable formula from real analysis course of the first year of education. We need that this transformation is invertible and is bijection. Yeah? So in our case, it is true. Only what we need to discuss that now dy is equal to determinant. Here is absolute value determinant of b dx. Yeah, this is now Jacobian matrix. Yeah? And then what we have, finally we get the following. It will be the integral. This remains to be the same. Here is I like multiplier. Here is a multiplier and exponent minus 1/2 of u. Here we can say that we have here norm of b minus 1 y minus c. Yes, this is exactly the expression of our x through the new variable y. And here we have one determinant of b, and then we have dy. Due to this, one can conclude that, of course, our new vector has density, because the probability that our vector belongs to something delta is expressed as an integral from some non-negative function over the set delta. So let us write the obtained density and discuss it. We have density q of y, which is equal, let us collect things in the right order. Here this multiplier, and here is determinant of b, and here is e minus 1/2 of a norm of b minus 1, y minus c, and here is square. Okay, we have such an expression for the density, but this expression is not satisfactory because it is expressed in the terms which are extra for our Gaussian vector. What? We already said every Gaussian vector has distribution which is uniquely defined by two parameters, mean and covariance. So let us express this density in terms of mean and covariance of new Gaussian vector eta. We know now that eta has the following parameters. It is normal. It has normal distribution with the mean C, and here we must place the following operator B star. Yeah. So the covariance of this vector eta is the product of two operators. Now we have A, which is equal B on B star. And what we have to do with this? We want to express these things in terms of operator. And here, let me recall you such a well-known, very useful fact that any operator, even if it will be a Hilbert space, but now we have a finite dimensional case, have a polar decomposition. Polar decomposition. Namely, I will write the formula for density. We remember it. And, namely, our operator B can be expressed as follows. B is equal to the following. We have some T and U. Here. U again is orthogonal operator. We discussed it. What is it today already? And T is the diagonal. T is just certain. Oh, no problem. T is self-adjoint operator. I do not need. Okay. T is self-adjoint operator. So we have such a polar decomposition. Why it has name polar? It is evident because U plays a role of the rotation, and this self-adjoint T, we remember in some basis this diagonal. It reflects how this operator make increase the length or shrink the length of the vectors. So we have such a decomposition for any continuous linear operator in Hilbert space. In our case, in Rn, and it is not very hard to find such decomposition. So please do this by exercise. And as an exercise by yourself. I will use this. This decomposition is unique. I will use this decomposition applied to this formula. Then what we get? Let us substitute this one to this formula. Then we will get the following expression. that A will be equal to B multiplied on B star, which is equal to T U multiplied by U squared U star T, because when we take a joint operator to the product, we just change an order of the product and put stars, but here we have this case. And then one can continue, and it is T squared. So one can see that our H can be expressed in this way with some self-adjoint operator T. Moreover, now let us discuss the determinant of A. Yes. From the last expression, I can say that determinant of A is equal to determinant of T squared and is equal to determinant of T squared. This is from one side. From other side, let us discuss determinant of B. Due to this, it is equal determinant of U multiply determinant of T. And let me recall that since U is orthogonal matrix, its determinant is equal to 1 or minus, or either or 1 or minus 1. This is a reflection of changing of orientation of the space under our generalized rotation. Yes, you remember that if you take just a rotation in R2, then the determinant is equal to 1. But if you make the symmetry reflection with respect to, for example, the line x equal to y in the two-dimensional case, then determinant is equal to -1. You change orientation. Exactly the same happened in general case. So this multiplier is equal plus -1 depending on structure. Since then, I can write the following relationship that we have now absolute value of determinant of B equal to absolute value of determinant of T from the polar decomposition of this matrix B. And having in mind this, one can say finally from here and here, so we have this plus this, that the determinant of B, absolute value of determinant of B, is equal to square root of determinant of A. It is a good sign because determinant of B rests in our formula for the density. So now we can express it in terms of initial covariance matrix for our Gaussian vector. This is one step. Another step must be done relatively to the expression in the power of exponent in the expression for the density. Let us do this. You remember we have the following. We have the norm of b minus 1, and here is y minus c square. Let us continue again using this polar decomposition. It will be like norm. Again, you remember that b is equal to u. Yes. Then, when I take b minus 1, again, I have to change order and say that it is equal to the following. Yeah. So let me continue with this expression instead of b minus 1. Then I will get u minus 1, t minus 1, applying y minus c here. Then you can check that this operator u minus 1 also is the rotation. Since then, it keeps the norm, and when calculating this norm, I can forget about this multiplier and simply write that it is equal to norm of t minus 1 y minus c square. It's equal to, now let us write this as a scalar product of this vector on itself. Then we will get that it's equal to t minus 1 y minus c, t minus 1 y minus c. What I will do, I will take this operator to this side. I can do this because t is self-adjoint, t minus 1 self-adjoint. So I will just write it as follows. It is equal to t minus 2. Here is y minus c, and here is y minus c. And finally, let us recall that now we have a relationship A is equal to square. Then I can put here A minus 1. I will do this just erasing B. And here is A minus 1. It's also a good sign because we are able to express the density of our vector finally in terms of its covariance and mirror. Let us write again the final formula for the density. Namely, we have the following: q of y is equal 1 divided by square root of 2 pi in n power. Here is square root of determinant of covariance matrix, and then the exponent. And here is the quadratic form generated by the inverse of covariance. This is the expression for our density. One can ask when it is valid. And maybe you see here the requirement that A is inverted. And it is true, this formula is valid in case when eta has a standard normal distribution with covariance matrix such that let me write it as follows. A is greater than 0. You remember that covariance matrix must be a negative operator. So when it is non-degenerated, strongly positive operator, then one can have the following formula for the density of Gaussian vector. By the way, it is firstly, it is very similar to the one-dimensional case, and so it is easy to keep it in memory. Let me call you if you have zeta. If you have just one-dimensional case and you have a normal distribution with parameters a and sigma square, then it has density like 1 over square root of pi, sigma, which is square root of sigma square, multiply exponent 1/2. Here I will write it as follows. Sigma minus 2 multiplied on x minus a square. You see, exactly, sigma square plays a rule covariance. We have square root of determinant, and we have inverse of covariance. We have inverse of variance. Yeah. So this is exactly the same what was written in one-dimensional case, but for us, there are another very important conclusions. The density which we obtain has a lot of good properties. You see, it is easy to check that function Q, we will use it in the future, belongs to the space of rapidly decreasing infinitely differentiated function on Rn. Yes. Also, Q is strongly positive on Rn. This is very important because it means that the support of this distribution, support of this normal distribution, CA now, is exactly R. Okay, we know this from the representation of density. And now let us switch to the case when determinant of A is equal to 0. What can we do in this case? Let's try to do something. Again, let us consider vector eta, which has normal distribution with vector C and A. But now we know the determinant of A is equal to 0. What we can do? Again, let us try to get this eta as an image of the standard Gaussian vector. One can do this using the following. Let us consider A, it is positive, non-negative. So one can define square root of A. What it is? It is self-adjoint matrix such that when we multiply it by itself, it will be equal to A. Then I will take it as a B, and now consider psi, which is standard Gaussian vector. With zero mean and identity covariance. Then consider the following vector: A 1/2 of psi plus C. And one can check that it has the same distribution like eta. So it is distribution with parameters A and C. Now, what we can say from this representation? What we can say from this representation? Let me recall you that we know already that psi has a supporter distribution on Rn. But now this operator shrinks Rn. Yes. So let us define A is an image of Rn under the operator. By the way, now again, let's use a privilege of finite dimensional case. It is exactly A. And what we know that it is a linear subspace of Rn, and due to our condition that operator A or this one is degenerated, now we know that dimension of L is less than n strictly. Yeah, because this operator, this one, kills some vectors. So now one can say that with probability 1, this vector A 1/2 of psi plus C belongs to the L plus C. Yes, this is like a shift of our linear subspace. Yeah, shifted. But it is easy to recall again from analysis first year that now Lebesgue measure this set, Lebesgue measure in Rn of A plus C is equal to 0, exactly because of dimension is less than. But we have this relation. So we now understand that if our Gaussian random vector has a degenerated covariance, then it must be concentrated on some affine subspace which has Lebesgue measure 0. So in this case, A, the determinant of A is equal to 0, then eta has no density. It is concentrated on the subspace, affine subspace, which has smaller dimensions than n. That is what we can say about the distributed density of Gaussian random vector. For today, this is all. And if somebody have questions or comments, please.
Does it have a density with respect to another measure, like a Hausdorff measure?
Exactly. Thank you for the question. Exactly. One can consider the Lebesgue measure here, or Hausdorff measure, if it is more convenient to say this. But Lebesgue measure here, lambda m, where m is dimension. And then, of course, with respect to this one, it has density in this subspace. Yeah. So thank you for the question. It is a good remark. We can say that due to this property, any Gaussian vector in Rn has such kind of support of distribution. So this A plus C, L plus C is equal to support of distribution of eta. And by the way, this is a good property of Gaussian random element in any Banach space too. Okay, thank you. Another questions, please. If there are more questions, thank you for attention and see you next week. Bye.